Have you ever found yourself staring at just a completely dense wall of C++ code,
Oh, absolutely.
like specifically for a math or graph library, and you realize that you're essentially just entirely guessing at what the algorithm actually does?
Yeah, you're just looking at endless underscores and nested parentheses.
Right, and asterisks everywhere just to
Mhm.
start a simple fraction. You're trying to, reverse engineer this complex mathematical concept that the original author probably understood perfectly in their head.
This just doesn't translate to the page at all.
Exactly.
Yeah.
So, welcome to today's deep dive. Today we are exploring a 2026 presentation by developer at Looks036, which is titled Visualizing C++ Doxygen Equations and Diagrams.
It's a really fascinating piece of source material.
It really is. Our mission today is to unpack how to transform that completely impenetrable code into beautifully rendered, browser-friendly visual documentation. And the best part, doing it without drowning in heavy dependencies.
Which is usually the biggest hurdle, right?
Totally. Okay, let's unpack this because, usually the idea of documenting code sounds like an absolute chore. But this source material reveals a way to make it genuinely visual and, honestly, pretty satisfying.
It represents a fundamental shift in how we approach code communication. We're moving away from just trusting the raw text of the code,
Right.
and we're shifting toward immediate, intuitive visual verification.
So before we get into the technical mechanics of exactly how this is done without the heavy software, let's establish the core problem. Like, why does text-only code fail us so badly when it comes to math and algorithms?
Well, it comes down to a well-studied psychological concept called cognitive load.
Okay, tell me more about that.
So, when you're reading raw C++ syntax for a complex formula, your brain is essentially forced to do double duty. First, it has to parse the syntax itself.
Like finding the variables and pointers.
Exactly. Identifying variables, pointers, figuring out the order of operations from all those brackets. And then secondly, it has to hold that entire syntactic structure in its working memory.
Oh, wow. That sounds exhausting.
It is. And simultaneously, it's trying to translate all of that back into the pure mathematical concept it represents.
It's kind of like reading sheet music without ever hearing the song actually being played.
That's a perfect analogy, actually.
Like, the notes are technically all there on the page, but you can't hear the melody. You're exhausted before you even figure out what the math is trying to achieve.
That is exactly it. This double duty creates a massive cognitive tax. So what's fascinating here is what Look036 proposes.
Right, which isn't just adding more text comments, I assume.
No, because that just adds more reading. The modern solution is using Doxygen to render actual scalable vector graphics, SVG diagrams, and standard latex formulas directly in the browser.
I have a specific question about that, though. Does adding visual documentation fundamentally change how a user understands the code? Or is it just, an aesthetic coat of paint?
Oh, it fundamentally changes it. When the formula is rendered beautifully in standard mathematical notation, your brain instantly recognizes the math.
So you don't see the asterisks and underscores anymore.
Precisely. You see a properly formatted mathematical fraction, exactly as it would appear in a textbook. The cognitive load drops dramatically because you aren't parsing syntax anymore. You are simply comprehending the logic.
It bridges the gap between the theory and the code base.
Exactly.
Okay, so visual clarity is obviously the goal here. But let's look at the biggest offender of cognitive load, which is complex math equations.
Yes, definitely the biggest offender.
Anyone who has tried to add math rendering to their docs knows it usually comes with a huge catch. Typically, it means downloading half the internet just to get your documentation to build.
Which breaks your build pipelines all the time.
Right. But the setup in this presentation avoids that entirely.
Mm-hmm.
How are they doing this without breaking the build?
That is where this methodology really shines, because historically, setting up server-side latex rendering is notoriously brittle. Well, usually to render math into an image, your continuous integration server, the system building your software, has to download massive gigabyte-sized latex toolchains.
But this presentation has a shockingly simple setup. It relies on literally one single setting in the Doxygen configuration file.
Yep, just setting use math jacks to yes.
And for the syntax, they just use a specific tag, like the @$$ for inline math and @ for display block math.
It's incredibly straightforward.
And because it relies on a MathJax content delivery network, a CDN, there is zero installation required. No heavy latex software, no Python build scripts.
Right, and to understand why that's so revolutionary, we need to think about the mechanism of a CDN, By using MathJax over a CDN, you shift the entire rendering burden away from the build server.
And it goes directly into the user's browser, right?
Exactly.
Here's where it gets really interesting to me. It's like packing for a trip and realizing you only need to bring a toothbrush, not your whole suitcase, because the hotel already has everything else.
I like that. The server just passes along the raw text strings, and your browser acts as the engine, doing all the heavy lifting to draw the equations in milliseconds.
It makes perfect sense. But taking away the heavy machinery doesn't mean it's flawless. The source material highlights a really specific, major pitfall that developers run into here.
Ah, yes. The dreaded \operator name command.
Right. The presentation specifically warns that if you use operator name to write out your math functions, you might completely break the render.
This is a very common mistake.
And the fix is to always use the \mathrm command instead.
Mm-hmm.
Right. Specifically for multi-letter function names, because it's a core text primitive that's guaranteed to be available.
Yes, Mathrm is the safe bet.
Wait, I'm going to push back here. If Mathrm works perfectly and is basically guaranteed, why do developers even fall into the operator name trap in the first place?
Yeah.
Are they just being stubborn?
No, it isn't stubbornness at all. It's a byproduct of how developers work on their local machines versus how a lightweight browser operates.
Okay, unpack that for me.
Most developers who write complex mathematical code have a full, robust LaTeX distribution installed locally on their own computer.
Right, their local environment.
Yeah. And when they are writing a formula and testing it locally, their system automatically loads a bunch of rich extensions in the background. One of the most common is the AMSmath extension.
So it's basically like an add-on dictionary of complex math symbols they already have downloaded.
Exactly. And in that rich, heavy local environment, operator name is the absolute standard way to write functions like sine or cosine. It automatically handles the spacing beautifully.
Oh, I see. So the developer gets used to this luxury standard.
Yes. And because it works perfectly on their machine, they assume it will work perfectly everywhere else. That is the trap.
They assume the browser has the same dictionary.
Precisely. But remember, MathJax via a CDN is highly streamlined for speed. It absolutely does not load every conceivable extension like AMSmath by default.
So the browser tries to read operator name, doesn't have the dictionary, and the render just breaks.
It's a classic case of it works on my machine. By forcing yourself to use Mathrm, you are ensuring that you rely only on the bedrock foundation of text typesetting.
You're writing for the actual medium.
Exactly.
Okay, so that covers the math equations. But since we know visual clarity is the goal, we have to talk about flow. Math formulas tell you the what, but algorithms are about the how.
Right. To understand the how, you have to move from static equations to structural diagrams.
And to draw this map, the presentation shows another surprisingly simple setup. You just set a flag called #to_yes.
Yep, that's the trigger.
Then developers write these @dot and @end.dot blocks directly in the code. Doxygen takes those, sends them to GraphViz, generates an SVG, and embeds it as an iframe.
GraphViz is incredibly powerful here. It takes abstract text relationships and calculates the optimal spatial layout automatically.
The examples in the source are striking, like the conjugate gradient iteration or the negative cycle detection.
The negative cycle one is a great example.
That's where it clicked for me. Visualizing the math, where it literally says 2 plus 3 plus -6 equals -1, which is less than 0, meaning boom, negative cycle.
It transforms abstract logic into a tangible geometry right in front of you.
But they go a step further than just drawing boxes. They engineered a standardized semantic color palette.
This is a really crucial part of the methodology.
Like they created highly specific hex colors. A pale blue #A9CCE3 is always for input and output. A slightly different blue #D4E6F1 is for process steps.
And pale green for success or converged states.
Right, #D5F5E3, yellow for warnings. And a pinkish red, #FADBD8, always means an error or infeasible state.
They even color-coded the edges. Valid transitions are green, invalid ones are red.
It's like standardizing a traffic light system for an entire city of developers. But let me ask you, is it really necessary to dictate the exact hex code across every single file? Doesn't that restrict creativity?
Well, if we connect this to the bigger picture, restricting aesthetic creativity is exactly the point. When you are reading highly technical documentation, you do not want creativity in the formatting. You want consistency.
So you don't have to guess what a color means.
Exactly. By standardizing these semantic colors, it entirely removes the need to read a legend. When a user sees a pinkish red node or a bright red edge, They instantly subconsciously register an error.
It just becomes a visual reflex.
Right. It drops the cognitive load again because the color itself acts as a piece of data.
Okay, so standardizing a diagram in one file is a neat trick. But the true test is whether it survives contact with a massive ecosystem. Let's look at the scale up.
This is where it gets really impressive.
The methodology was applied across 21 different C++ projects. They changed over 70 files with a single migration script.
The before and after impact there is massive.
It really is. Theme engines moved from Python to Doxygen HTML. CI dependencies like TextLive, Divas VGM, and Jinja2 were entirely removed.
Yeah.
Network dependencies went to zero.
It's a radical simplification of the infrastructure.
It's like replacing a noisy, polluting factory with a single silent solar panel. But here's what I want to know. If taking away all these heavy back-end dependencies is this effective, why isn't every library maintainer doing this right now?
Well, you have to understand the sheer inertia of legacy systems and the absolute fear developers have of touching their CI pipelines.
Oh, really? Just fear of breaking things?
Exactly. Setting up a continuous integration pipeline is often incredibly painful. Once it works, maintainers are terrified to modify it. Breaking the main build halts all development for everyone.
So how did this presentation solve that?
With a very elegant failsafe. Crucially, instead of forcing Doxygen as a dependency, they used the command find package, specifically with the Doxygen quiet flag, plus an IF statement.
So if Doxygen isn't there, it just stays quiet.
Precisely. It tells the server, if you have Doxygen, great, generate the docs. If you don't, do not throw an error, just build the core software and ignore the documentation.
Oh, wow. So you don't break the main build if Doxygen isn't present. That completely removes the risk.
It slips into the code base without triggering any alarms.
Okay, so the factory is sleek and efficient now. But how do we automate the actual labor of writing these visual docs? I mean, writing math syntax across 21 projects still sounds tedious.
Yes, and that brings us to the creation of reusable AI agent skills.
Right. The source details two automated skills. Add CPP and add CPP.
And these are really fascinating.
The eCoon skill scans C++ headers, identifies math functions in domains like linear algebra or root finding, and adds the formulas. And the dot skill scans for graph algorithms and adds the diagrams.
Using the exact templates and color palettes we just talked about.
The metrics of success here are wild. 28 formulas added to RATTRIG CPP, which is rational trigonometry, over 20 added to Alago CP for convex optimization, plus major additions to other complex libraries.
It's a powerful proof of concept.
It's like having a robot assistant who reads your dense academic manuscript and automatically draws the perfect illustrations for it. But here's a challenge. If an AI agent is scanning the code to write the documentation, how do we ensure it captures the original intent of the human who wrote the algorithm?
That is the big concern.
Right. Like, how do we know it's not just mindlessly translating raw syntax?
This raises an important question, but the key is that these agents are not operating in a vacuum. They operate strictly within the structural guardrails created by the developer.
You mean the rules we've been talking about?
Exactly. The human established the mathrm rule. The human engineered the strict hex palettes. The AI is simply mapping the code onto that pre-existing framework.
So the human sets the framework and the AI just scales it.
Precisely. It ensures visual consistency across hundreds of files at a speed a human just couldn't match.
Okay, as we wrap up this deep dive, let's quickly distill the core takeaways for you listening. We've seen the elegance of Doxygen plus MathJax for zero dependency rendering.
And the power of SVG at-dot diagrams to map out complex flow.
We highlighted the crucial mathrm fix over the operator name trap.
We discussed the brilliance of a standardized subconscious color palette.
And of course, the safe CI integration using that quiet failsafe.
Oh,
Ultimately, whether you are managing a giant open source library or just trying to make your own personal scripts readable for next week.
how you visually present your logic is just as important as the logic itself.
Absolutely.
But it does leave us with a final thought to ponder.
Oh, what's that?
Well, building on these sources, if AI agents can now automatically generate flawless visual flowcharts and perfectly typeset mathematical proofs from raw C++ code,
Yeah.
will we eventually reach a point where developers stop writing human-readable comments entirely?
Oh, wow.
Will we just rely purely on real-time browser-rendered visual translations of the machine's logic? It's something to think about the next time you're trying to decipher an algorithm.
That is a wild thought to end on. Thanks for joining us on this deep dive, and we'll catch you next time.